just a short video introducing graphs in computer science, their benefit, use cases, some terminology, and then how we actually even represent graphs in code. So here's our graph, which is a bit confusing. You're like, no, that's not a graph. That doesn't look like, you don't see that X and Y axis that you're used to seeing, right? So it's a bit confusing. This is a graph both in mathematics and in computer science. A graph is really a collection of vertices with edges that are connecting those nodes or those vertices. Here's a graph of some make-believe airline called Northwest Airline and their flights, showing that Boston, shockingly, doesn't fly into Atlanta, one of the largest hubs, but Atlanta flies to Austin, Austin flies to San Francisco somehow doesn't fly to Seattle, but Seattle, they can fly to Anchorage, Alaska, or to Minneapolis, right? This is a graph showing these vertices, which in this case are cities, and showing the edges or the flights that are connecting those cities. We can also have a graph representing a computer network or the internet, showing how these nodes, so nodes can be all kinds of things, or these nodes, the vertex. So this vertex, the set of nodes, it could be landmarks and the roads that connect them, cities, the flights that are between them. Here we could have networks and their connections, wired or wireless, many different representations of graphs. And when you begin to think about any type of objects that are connected physically or otherwise with other objects, we can realize that graphs is a huge, huge data structure with many applications. Arguably one of the most famous problems in graphs is called the traveling salesperson problem. That this traveling salesperson needs to start at some city, at some vertex, and visit all of the other cities, and then ultimately return back home to their starting city. Like literally an actual traveling saleswoman, she needs to start in maybe Texas in some city and travel all around those different cities and ultimately return home. Why is it a famous problem? Because you want to do it in the most efficient manner, right? You don't want to go backtracking and revisiting cities when you don't need to visit them again. And ultimately, you want to get back home in the most efficient manner, optimizing gas, optimizing travel time. A very famous problem on graphs. So let's talk about some terminologies regarding graphs. So here we have a node as a vertex. And we also have edges that are between these nodes, and these edges can have a weight. So a graph is really a set of vertices and edges where I say graph is VE, where V is a set of vertices, E is a set of edges that are between those vertices. So in particular, or in specific, an edge is, we have this pair UV that is connecting two vertices. Here is an example of a graph. So we have A, B, C, D, E are our nodes, our vertices, and then we have the edges that are connecting them. So we have an edge from A to B, we have an edge from A to C, an edge from A to D, an edge from C to E, another edge from D to E, and so on. What is a directed graph? What is an undirected graph? Here's an undirected graph where the edges have no direction, right? Versus a directed graph, you can think about this as a road network, right? Some roads you can go in both directions, such as we would see right here. Other times, like in big cities, you'll have one-way roads. So this would be a directed graph showing that there's really only one way to go from this vertex. A vertex could be just an intersection. To go from this vertex to this other vertex. And on this road, there's only one way. On this road, there's only one way. On this road, anything goes, or at least those two ways go. So here we have a directed graph versus an undirected graph. What is a subgraph? More terminologies. A subgraph is really just a subset of vertices and their respective edges. In the same way that we have a tree and a subtree, pretty straightforward. Here is a subgraph. The idea of a simple path, again, just a lot of terminology, basic terminology. A simple path is a path such that all vertices are distinct, except that the first and the last could be the same. So here, if we have this graph, it's clearly an undirected graph. A simple path would be A, B, C, D, right? It says that all vertices are distinct, except the first and the last could be the same. So I could say, what about A, B, D, A? Is that a simple path? The answer is yes. A, B, D, A, all vertices are distinct, with the one exception that maybe the first and the last vertex can be a repeat of one another. What about A, B, C, B, D? That's clearly not a simple path because we repeated B. This is the idea. It's the basic term here. What is a cycle? A cycle is a path that starts and ends at the same vertex, at the same node. For an undirected graph, the edges, of course, will be distinct. So here we have a cycle from C to D to B back to C. So when we end at that same vertex where we started, that is called a cycle of graph terminology. Connected versus unconnected, pretty straightforward. Here's a connected graph, here's an unconnected graph. Not a whole lot more to say in that regard. What is a DAG? A directed acyclic graph is what you see here. We have a directed graph with no cycles, because you're going to see, and we're going to learn with algorithms, there are so many famous algorithms that require no cycles in the graph. So now we have a specific term. We have a graph that is directed with no cycles. It is a directed acyclic graph, not having any cycles. A weighted graph. Now we're beginning to perhaps see how graphs can link to maybe a road network or landmarks. Here, to go from this location to this location, let's say it's 10 miles. To go from this location to vertex 3 or node 3, whatever that object is or location is 4 miles, right? So we put a weight on the edges to indicate maybe distance, maybe time, maybe hop, maybe cost, the cost of traveling over certain edges. The domain of graphs and their problems is huge and extremely vast. What is a complete graph? A complete graph is a graph where there is an edge between every single vertex. And the total number of edges in the graph would be this. Does that make sense? If there's a graph between every single vertex, well, think about this. How many vertices do you see here? You see 4 vertices. Well, if there's 4 vertices and there's a graph between every single edge, how many edges will be emanating from or will be leaving a particular vertex? Meaning, if this one vertex here has to be connected to all of the other 3 vertices, that means there will be 3 edges leaving this vertex, right? Well, there's going to be 3 edges leaving this vertex, 3 edges leaving this one, 3 edges leaving that one, but they're not distinct, right? They're not distinct, so you can't say, well, how many edges do I have? I have 3 edges leaving each one of these vertices. I have 4 vertices. 3 times 4 is 12. Do we really have 12 edges? If you count them, 1, 2, 3, 4, 5, we have 6 edges. What's the math? We take the number of vertices, 4, times 3, which is 4 minus 1, get 12, divide that by 2, and that is your total number of edges in a complete graph. What is a sparse graph? A sparse graph is a graph with a very minimal number of edges in the graph. In fact, if we want to have a sparse graph, the sparsest of sparse graphs, that is at least fully connected, that would mean what? That we would have n minus 1 the number of edges, right? So how many edges would we have? Well, if we have 4 vertices, we would need 3 edges connecting those vertices. What really remains, it's not even been 10 minutes, what really remains is just talking about how do we actually represent graphs in our code. And it turns out there's 2 representations, adjacency matrix and adjacency list. We need to understand both of these perfectly and understand the nuances and the advantages and disadvantages of both of them. In adjacency matrix, it's really just a two-dimensional array. Let's assume that we have n nodes in our graph, so we're really going to have an array of size n by n. Let's call the array A. It's going to go from index 0 to n minus 1, the number of rows, and for each row, there will be from 0 to n minus 1 cells. If vertex I and j are connected in the graph, well, the array A at index ij will equal 1. Otherwise, array at index ij will equal 0. Also, if the vertex has a loop, what is a loop? Is when a vertex connects to itself. If a vertex has a loop, then the array A at index I, so maybe at row 4, column 4, it would, for example, equal 1, indicating that loop. If there is no loop, the array A at row I, column I would equal 0. So here's an adjacency matrix. It's easiest just to pause without explanation and examine this matrix. Just pause the video, spend 60 seconds, 2 minutes, look at it, see if it makes sense how this particular undirected graph maps into this matrix. Pause the video, come back. So here we have this particular undirected graph. Here is the adjacency matrix representation of that graph. We have 4 vertices, therefore we're going to have 4 columns from 0 to 3, and 4 rows, and we're going to have for each row 4 columns from 0 to 3 as well. So notice in the graph, we see here that 2 is connected to 1, right? So at row 2 and column 1, we should see a 1. But also at row 1 and column 2, we should also see a 1. What about we notice that 0 is connected to 2? So at row 0, at column 2, we should see a 1. Also at row 2, column 0, we should see a 1, right? Because since this is an undirected graph, if 3 is connected to 1, well, 1 is also connected to 3, right? So if 3 is connected to 1, that means we're going to see a 1 right here. And then row 1 is connected to 3, we see a 1 right here as well. Finally, notice we don't have a connection between 0 and 3. So we come to row 0, column 3, no connection. And then we come to row 3, column 0, no connection. What are the other zeros that we're showing in this matrix? Are right here, we're showing that 0 is not connected to 0. There's no loop at 1, 1. There's no loop at vertex 2, and there's no loop at vertex 3. Some takeaways. When we have an undirected versus a directed graph, an undirected graph is going to be symmetric, meaning whatever value stored in the array at index ij will be the same value that is stored at index ji, versus a directed graph, when we're indicating direction, there's no guarantee of symmetry in that directed graph. So here we notice this is let's call it a one-way road network where every vertex is linking maybe to some other vertex, but it's not going back, right? 0 is going to 2, but 2 is not going to 0. We have 1 going to 3, but 3 is not going back to 1. What's the takeaway? Well, if you look at 1, we can see it's connected to 3 because 1 is going to 3, but 3 is not going back to 1, right? Also, if you look at 0, 0 is going to 3, but 3 is not being connected to 0. So this is the representation of here we have what? An undirected graph as an adjacency matrix. Here is a directed graph as an adjacency matrix. And finally, a weighted graph. Pause the video. It doesn't require a lot of thought to make sense of this. Here is a weighted graph. Pause the video, 15 seconds, come back, make sure you're good. What's going on here? What we're storing in this particular adjacency matrix is in this two-dimensional array is simply the weights of the edges, as opposed to a binary of just 0 and 1, where 0 means there's no connection between two particular vertices, 1 means there is a connection. Now on a weighted graph, we're actually storing the weight. So 0 means there's no connection, but any other number means there is a connection, And this would be the weight of that connection, whether that weight, again, is time, hop, distance, or what have you, cost. So here we would say the weight from 0 to 2 is 10. So from 0 to 2 is 10. But we also have from 2 to 0 is 10. What about from 1 to 3? Well, from 1 to 3 is 5. Also from 3 to 1 is 5. Because this is a weighted graph, but it's also an undirected graph. So we have that symmetry. Now, what about if you had a weighted graph, but now it's directed? How would that look? You'd have to think it'd be the same thing. You just would not have that symmetry. So if, for example, we had 1 going to 1 going to 3 at a cost of 5, as you see here. But if 3 did not go back to 1, this 5 would simply be a 0. So here we have a weighted graph that is undirected, therefore we have that symmetry. Of course, that symmetry is not guaranteed on a directed graph. The other type of representation is called an adjacency list. This is really just an array of lists. From a Java perspective, you could say an array of linked lists. The ith element of this array, so here's the array right here, the ith element of this array is really just a linked list that shows the values or the vertices that index I is connected to. So here, without even looking at the graph, this is a graph because it's a graph representation. We know that vertex 0 connects to vertex 1, 2, and 3. Vertex 1 connects to vertex 3. Vertex 2 connects to vertex 3. And vertex 3 does not connect to anything. This is a directed graph as well. So here is that graph. So 0 connects to 1, 2, and 3, as we see. We have 1 connecting to 3. We have 2 connecting to 3, and we have 3 not connecting to anything. What about a weighted graph as an adjacency list? So here's where it's a little bit different, because not only do you need to store the weight, but you need to store what vertex it's connected to. So look here, if we see that 1 is connected to both 3 and 0, so 1 is connected to 3, 1 is also connected to 0, but now we need to store their weights. So when 1 is connected to 0, it's connected to 0 with a weight of 10. When 1 is connected to 3, it has a weight of 4. And you might be thinking, well, why do we have to show which vertex? Can't we just show the weights? Well, think about that. If 1 was only connected to 10, the weight, and 4, the weight, which vertex is that? Which vertex really, 1 connected to 10, which is a weight of 10, but really, which vertex is it connected to? So you have to actually augment the actual field to indicate what it's connected to and its weight. So here we see that 2 is connected to vertex 0 with a weight of 20. As we see, 2 is connected to vertex 0 with a weight of 20. But also 0 is connected to 2 with a weight of 20. And if we continue with 2, 2 is connected to vertex 3 with a weight of 5. 2 is connected to 3 with a weight of 5, and so on. So now we see we have adjacency matrices, that two-dimensional array, where we almost have like a binary 1 or 0 to indicate connection, or if it's a weighted graph, 0 indicates no connection, and the weight is what is stored in the array. We have that symmetry that you can identify quickly if it's undirected, or if it's even directed, you can check, can you go down both ways of that particular street by checking that symmetry of a particular position. And then now we have this adjacency list, which we have an array of linked lists. There's pros and cons to each. We want to fully understand the advantages and the disadvantages of these two representations. And believe it or not, last slide. This is a quick one, but we really want to, again, make sure we understand the pros and cons of these different representations. So here, what if we ask you to, given two vertices, U and V, find out whether U and V are adjacent. Find out whether those two vertices are connected. Just in code, forget. In a picture, you can easily look and see if they're connected. But in code, given either of these representations, given a vertex U and some of the vertex V, determine whether or not they are connected. Well, if you're using an adjacency matrix, that's O of 1, because you're just going to go to index U, index V. If it is non-zero, they're connected. But what about an adjacency list? How would you determine if two vertices are connected? Well, you'd have to go to index U of the array, and then you'd have to traverse over the linked list at index U. What is that linked list, right? That linked list at index 0, for example, this list right here represents the vertices that index 0 is connected to. So all of a sudden, if I want to check what is the speed or the running time of determining if U and V are connected, I would actually have to go to index U of the array of the adjacency list and then traverse the entire linked list at that array. How long would that linked list be? The answer is it would be the degree of that particular vertex. That's a new term I did not actually define. The degree of a vertex or the degree of a node is the number of edges that are extending out from that node. So here, if you have a given node and 8 edges are leaving that node or coming into that node, right? 8 edges are emanating from that node, the degree of that node would be 8. So what is the running time to determine if two nodes, U and V, are connected, if two vertices are connected? Well, we have to go to index U of the adjacency list, and then we have to traverse over the entire linked list at index U. And what is the size of that linked list? It's how many connections, how many edges were emanating from vertex U. So it would be the degree of that particular node. What about given a vertex U? Identify all of the neighbors of vertex U. Given some vertex, find all neighbors of that vertex. What's the running time? Well, on an adjacency matrix, what would be that running time? And I want to come over here to the tablet to actually just look at another graph. Here we have a directed graph. And imagine if I said, and you know what, let's even back up. Before answering that question, just examine this graph, right? So we have this graph here. It has 6 vertices. Here we have the 2 representations. We have the adjacency matrix. We have the adjacency list, right? So we can see, let's pick a particular node. What would be an exciting one? None of them have a lot of connections. Let's look at node 3. So we have here vertex 3. Vertex 3, we have 3 edges leaving 3, going to 1, going to 2, and going to 5. So let's come here to row 3 of the adjacency matrix. 3 is going to 1, 3 is going to 2, and then 3 is clearly going to 5. 1, 2, and 5. Pretty straightforward. What about in the adjacency list representation? You see that right here. You go to index 3, which is right here, of the actual array. And at that array, at index 3, what do we find? We have a linked list of vertices that vertex 3 is connected to. And it's connected to what? It's connected to 1, to 2, and to 3. So here are 2 representations of this particular graph. Let's now answer this question of, given a vertex U, list out, enumerate out all of the neighbors of that vertex. So given vertex 3, what's the cost to list out all neighbors of vertex 3 using an adjacency matrix? Well, using the adjacency matrix, you have to actually iterate over that entire row. How long is that row? The number of vertices. You have to actually loop over that entire row and check. Are you a 1? You're a neighbor. Are you a 1? Well, we're connected to you as well. You're a neighbor. Are you a 1? No, you're a 0. Oh, we're not connected to you. You need to loop over that entire row, checking. You're a 1, yes. You're a 1, yes. You're not a 1, we're not connected, we're not connected, we are connected, we're not connected. So you're going to loop over the row, which is the length of the number of vertices. Whereas, if we now erase that and we come over and look at the adjacency list, what is the running time to enumerate all neighbors of a particular vertex? It's just the length of that list, which is what? It's the degree of vertex 3. So vertex 3 right here, what is its degree? It's 1, 2, 3, right? There are 3 edges that are emanating from vertex 3. That is the degree of vertex 3, and that is therefore the big O of the time to enumerate or list out all neighbors of a particular vertex would be O of the degree of that node. And finally, the last thing says, for all vertices, list out all neighbors of each vertex. What is that running time? So for every single vertex, meaning we would have to loop over all of the rows, and for each row, we have to loop over all of the columns, 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 all of the columns. So here, if we have n vertices, there are going to be n rows and n columns. Therefore, that is an O of n squared running time to determine all neighbors for all vertices. Whereas, when we look at the adjacency list right here, how does that perform? What is the running time to find all possible neighbors for the adjacency list? Clearly, we're going to need to loop O of n over the array where each index of that array contains a linked list of the neighbors. And so what's the running time? Well, it's really the summation of the degree of that node plus the degree of node 2 plus the degree of node 3 plus the degree of node 4 plus the degree of node 5 plus the degree of node 6. So it's really the summation of the degrees of all of the nodes. So that's really all this video is about: introducing graphs, talking about their terminologies, talking about the use cases of graphs, and then really understanding the different representations. What is an adjacency matrix? What is an adjacency list? Coming back over here to the tab, making sure we fully understand, given a graph, how to represent that graph as an adjacency matrix, how to represent this undirected graph as an adjacency list, also given a directed graph, how to represent that as an adjacency matrix and as an adjacency list, and then finally understanding the advantages and the disadvantages of both of these representations and their respective running times. Guess what? Let's go. We are done. Our daily demotivator perspective, less is more. Unless you're standing next to the one with more, then it just looks pathetic. It's not me. This is despair.com. Don't hate. They're great, though. It has been fun. As always, reach out if you need anything. Take care.